Large language models require a specific high-density server architecture. The hardware clusters used to train and run these models generate electrical loads that surpass the limits of standard data center cooling and power delivery. To quantify the operational strain, a single artificial intelligence query requires nearly 10 times the electrical load of a standard internet search. This chart plots global data center power capacity. We are currently at a baseline of 57 gigawatts. By 2030, that demand is projected to reach 122 gigawatts. Meeting this demand requires the industry to double the global power plant capacity dedicated specifically to data centers by the end of the decade. Current AI infrastructure requirements outpace legacy utility planning, making historical grid capacity forecasts and development timelines obsolete. The physical bottleneck lies in the transmission network. National grids rely on aging infrastructure that lacks the capacity to route these massive volumes of electricity into concentrated geographical hubs. In saturated markets like Ireland, network operators have responded by denying grid access or imposing connection delays that can exceed a decade to protect the stability of the public system. To deploy on schedule, high-density facilities must decouple their development from public grid dependence. Modern data center design integrates multi-megawatt on-site generation as a mandatory primary component rather than an occasional backup system. Because external power is no longer guaranteed, operators are engineering these facilities as sovereign energy nodes, relying on dedicated on-site prime movers to maintain baseload capacity. While data centers have traditionally relied on high-speed emergency diesel generators, these units are not engineered for the demands of a primary captive plant. High-speed engines operating above 1500 RPM degrade rapidly under continuous baseload operation. The resulting voltage and frequency variances can destabilize or damage sensitive microelectronics. Primary power requires a medium-speed reciprocating engine, designed to operate at less than 750 RPM for continuous duty cycles. This is the 5160 dual-fuel engine block. It operates at 500 RPM and is built for continuous power generation, with an operational life that can exceed 100,000 hours. Operating an isolated microgrid requires strict N+1 redundancy. To ensure 100% uptime, operators must mitigate the risk of a failure in the national gas pipeline. Dual-fuel capability allows the engine to run on pipeline natural gas and switch instantly to stored liquid fuels, such as hydrogenated vegetable oil, without dropping the electrical load or stopping the engine. A medium-speed dual-fuel architecture provides the only proven methodology for guaranteeing multi-megawatt baseload independence without compromising mission-critical reliability. Corporate renewable procurement relies heavily on wind and solar power purchase agreements, which introduce physical intermittency into the facility's power supply. Captive engines bridge this gap through rapid load following. As renewable input drops, the engine immediately increases output to maintain a stable server supply. These systems start in under 5 minutes, ramping output at over 40% per minute. Engines deploy in modular increments of 7 to 26 megawatts. This allows the power plant to scale alongside new server racks, preventing wasted capital expenditure. Captive engines provide the load-following capacity needed to make high-penetration wind and solar power mathematically viable for an isolated microgrid. Power generation is only half of the engineering requirement. The European Energy Efficiency Directive now mandates the physical recovery of excess heat for all data centers operating above 1 megawatt. To meet these standards, facilities must transition to trigeneration, the simultaneous production of electricity, heat, and cooling. This diagram shows the flow of thermal energy. Engine waste heat drives an absorption chiller to cool server racks. Next, exhaust heat from the servers is upgraded by heat pumps. This thermal energy is then injected into city heating networks or routed to thermal storage. Capturing and upgrading this heat increases total energy efficiency from approximately 50%. The Irish grid faces severe constraints. With new connections blocked and a reliance on a single gas pipeline from the UK, the facility requires high levels of self-sufficiency. The solution involves an array of 6 Everllence 18-cylinder 5160 dual-fuel engines. These engines deliver a combined output of 111 megawatts. The dual-fuel system ensures the data center can operate at full capacity even if the national gas pipeline is disrupted. In peak plant mode, the facility exports power back to the public grid during periods of high demand or low renewable generation, supporting national grid stability. This model transforms the data center from a consumer of grid resources into an active, stabilizing asset for the surrounding energy infrastructure. Modern data centers now operate as sovereign, fully integrated utility nodes rather than passive endpoints on a municipal grid. These medium-speed systems are already transitioning to run on hydrogen blends, paving the way for a zero-carbon baseload reality as hydrogen supply chains develop. The staggering computational power required for modern artificial intelligence necessitates a parallel, uncompromising commitment to on-site energy engineering. Tomorrow's data center functions as a thermodynamically looped power plant, where computation is one byproduct of a total energy optimization strategy.